In this class we are going to be talking about AVL trees. In the last classes we have seen the binary search tree data structure. Now one problem with the binary search tree, if you recall, is that the operations of insertion, deletion, search, all of them take time proportional to the height of the tree. Now the height of the tree can be very bad. Yeah, we saw an example where the height of the tree could be as bad as order n, yeah, or n minus 1. So we want to somehow create a tree which does not have too bad a height, and that is what we are going to do today. We are going to look at this data structure called AVL trees. Okay. Now what is an AVL tree? AVL trees are what are also called height balanced trees. Okay. Now ignore these white spots that are showing here, they should not have shown here. This is a binary search tree. These are the keys, inside the nodes are the keys, right. Everything to the left of the root is, everything which is less than the root is to the left of the root, and everything which is more than the root is to the right of it. Now what I have also written next to each node is the height of a node. Now what will we call the height of a node? We have not defined this term yet. We will just say the height of a node is the height of the subtree rooted at that node. Yeah. So for instance, if I look at this node, this is the subtree rooted at this node, right. What is the subtree rooted at a node? It is just the set of descendants. Yeah. So I am looking at this tree now. Now in the previous classes we had defined the height of such a tree as 2 and not 3, because we had said that this has this is level 0, this is level 1, this is level 2, and so we had called this the height of the tree as 2. Now we will just modify this. We will say that if it is a singleton node, just one node, it is height 1 instead of height 0 as we have been calling it. This subtree has height 2. So level numbers are now beginning, let us say, with 1. Okay. So this is height 2, this has height, this subtree has height 3, and this entire tree has height 4. Okay.
So this is with respect to definitions in AVL treatment.
Yeah. So we are going to call this the height of the tree for, let us say, for the purposes of AVL tree. So with every node I have put down the height of that node. So what is the height of a node? It is just the height of the subtree rooted at that node. Yeah. So this is height 1 because there is nothing below it. This is height 1, this is, so all the leaves will have height 1. The parents of the leaves will have height 2, and so on, you know. Yeah. Now such a tree is called a AVL tree if it is height balanced. Now what does height balance mean? If I look at any node and I look at its children, then the difference in their heights is at most 1. There might be no difference in their heights, as is the case with this node. Its two children have the same height. This node has a difference. The left subtree has more height than the right subtree. The left subtree has height 2 and the right subtree has height 1. This also has a difference of a 1. The right subtree has height 3 now, and the left subtree has height 2. Yeah. But the difference is no more than a 1. Right. So this is an AVL tree. This is what our definition of an AVL tree would be.
So this is true for each node of the tree.
Yes, it is true for every node of the tree. It is a binary search tree, so there are two properties. It has to be a binary search tree, and for every internal node of the tree, the heights of the children differ by at most 1. Why have I said internal? Well, for a leaf node, it has no children, so it does not make any sense to talk of the height of the tree. Right? For this node, the right subtree has height 1, and since the left subtree is missing, we call it height 0. So now you understand why I had to make this change today, right? Absence of a tree, I will call it height 0 now. Yeah, and a single node will now become height 1, and whatever, right? So that's why I have to shift the definition a bit. Everyone okay with this? Yeah. So let's see what is not a tree. What is not an AVL tree? One second, let me just My pen doesn't seem to be working. Okay, so let me just switch over to this thing. So recall that one of our binary trees which was very bad was, which had a huge height, was a tree like this. Yes, right. This is a binary search tree. I could put some keys so that it looks like a binary search tree, and this has height equal to n minus 1 if there were n nodes. Yes. Now, is this an AVL tree? No. Is this node height balanced? Yes, it's a leaf node. Right? Is this node height balanced? This is also height balanced. Is this node height balanced? No, because the right subtree has height 2 and the left subtree has height 0. So this has height 2 and this has height 0. So there is the height balance property is violated here. It's also violated here and it's also violated here. So we will never have such kind of trees as AVL trees. Okay, good. So let's try and figure out. So since we said that we are not going to have such kind of trees as AVL trees, let's try and figure out how bad the height of an AVL tree can be. Yeah. So let's say I have an AVL tree of n nodes. Yeah. If its height can still be as bad as n minus 1, I have not gained anything. So I would like to say something like its height is no more than a log n or some such thing. We'll figure that out. So that's what we are going to say. This is what we are going to prove in, let's say, the next few minutes. The height of an AVL tree T, which has n nodes in it, is only order log n. Okay, and let's see why this is true. So I'm not going to prove this claim directly. I'm going to make a slightly different argument. Right? I'm going to say, let's take an AVL tree of height h. Amongst all possible AVL trees of height h, let me see the one which has the smallest number of nodes. Right? So I define this quantity n of h here as the minimum number of nodes in an AVL tree of height h, and let's figure out what this quantity is, and then we'll see how this implies this proposition here. Okay, everyone understand what I'm saying? So given an AVL tree of height h, we want to find out what is the smallest number of nodes it has. Can it have only h nodes? Then we will be in trouble. Right? We want to say it has many more nodes. Right? If you recall, a binary search tree on h nodes of height h can have only h plus 1 nodes. Right? This example that I showed you, which was a path. But a good tree, which is like a complete binary tree of height h, will have 2 to the h nodes. Right? So what we would really like is that our AVL tree, which has of height h, have a large number of nodes, not just h, but more like 2 to the h, something like that. Yeah, and that's what we are going to prove. Okay, so let's understand what this quantity. It's the minimum number of nodes in an AVL tree of height h. So if I take an AVL tree of height 1, what's an AVL tree of height 1? Just a singleton node, nothing else. Right? So it has only one node in it. If I have an AVL tree of height 2, root and one node, but it can also be root and 2 children, right? So why have I written 2 here and not 3? Minimum. I'm counting minimum, right? So that's why n2 equals 2. The minimum number of nodes will be just 2 in an AVL tree of height 2. So suppose I have an AVL tree of height 3 or more. So it will contain one root node. So suppose the AVL tree has height h, it will contain one root node. It will have an AVL tree of height h minus 1 on one side and an AVL tree of height h minus 2 on the other side. Why h minus 1 and why h minus 2? Can someone tell me?
H minus 1 is due to the...
Well, it has height h, so its children can have height only h minus 1, not more than h minus 1.
Can have a difference of at most 1.
Right? So they can have a difference of at most 1. So if one of them is h minus 1, the other one can only be h minus 2 or h minus 1. Right? So one of the subtrees has height h minus 1 and the other subtree has height h minus 1 or h minus 2. But what will we pick? We would like that the other subtree have height h minus 2. Why? Minimum number of nodes. So a tree which has smaller height will also have smaller number of nodes. So we would like that the other subtree have h minus 2 height. Yeah. So if n of h was the number of nodes in the tree of height h, then what is the number of nodes n of h equal to? It is the number of nodes in the tree of height h minus 1, the smallest possible. So because we would like that the left subtree which is of, let us say, of height h minus 1 and the right subtree which is of height h minus 2, the h minus 1 subtree have as little number of nodes as possible, and the h minus 2 subtree also has as little number of nodes as possible. So the number of nodes in the left subtree is n of h minus 1, the number of nodes in the right subtree is n of h minus 2, there is one root node. So this is what the recurrence relation should look like, right. Once again we are seeing a recurrence relation. Everyone satisfied with this? Yeah. So this is what we have to solve today. Yeah. And what are the base conditions? We know n of 1 is 1 and n of 2 is 2. Right. With that you can figure out what n of 3 would be. N of 3 would be 1 plus 2, 4. Yeah, and so on and on. But we would like a closed form expression to be able to do this. So we will solve this recurrence. Okay. So we are not going to be solving this recurrence exactly. Okay, we are going to do an approximate solving. So first we use the fact that n of h minus 1 is only going to be larger than n of h minus 2, right? Because as the height of the tree grows, the number of nodes cannot reduce, right? It will only be more. Right. So n of h minus 1 is at least as large as n of h minus 2, and then this implies that what we had written earlier, n of h equals n of h minus 1 plus n of h minus 2 plus 1, this quantity is at least as large as 2 times n of h minus 2, strictly larger because I have also dropped the 1. Yeah, I have replaced this n of h minus 1 by n of h minus 2, and this is what I get. Yeah. And now this becomes a simple thing to solve. N of h is more than 2 times n of h minus 2. This is what I will solve. So n of h is more than 2 times n of h minus 2. Yeah. And now n of h minus 2 is more than 2 times n of h minus 4. So this implies this entire thing is more than 4 times n of h minus 4, which implies that the entire thing is more than 8 times n of h minus 6. Yeah. You understand how this comes? N of h minus 4 is more than 2 times n of h minus 6, and so on and on, which will eventually take us to something like 2 to the I after I steps n of h minus 2i. Yeah, great. Okay, so suppose I pick I equals h by 2 minus 1. I am going to assume for now that this quantity is an integer. Yeah. So let us assume h was even to begin with. So this is an integer, and for this value I will get 2 to the h by 2 minus 1, n of h is more than 2 to the h by 2 minus 1 times n of, so I am replacing I by h by 2 minus 1, so I get a 2 here. Yes. So it is n of 2, n of 2 recall was 2. So it becomes 2 times 2 to the h by 2. Is everyone with me? Right. So what does this say? We just argued that if your AVL tree has height h, then it has at least 2 to the h by 2 nodes, at least so many nodes, right. What is the maximum number of nodes it can have? 2 to the h, something like 2 to the h, either 2 to the h or 2 to the h plus 1, one of those. Yeah, because it can be a complete binary tree. Yeah. So now suppose I were to take logarithms, what would I get? I would get that h is less than 2 times log of n. Yes. Right. So if I have an AVL tree on n nodes, so right. So, yeah, n of h is actually less than our n, right, because I have an AVL tree whose height is, let us say, h, and it has n nodes, So suppose I had an AVL tree of height h and n nodes, then it will also satisfy this relation, yes? It will satisfy this relation because n is only going to be larger than n of h. N of h, what was n of h? N of h was this minimum possible number of nodes. Yeah. So any AVL tree on n nodes and height on n nodes has height at most log n, 2 log n from this example, from this argument. Is there something you did not follow? Are you confused about this n of h? Right. So this is what we argued after taking logarithms. Now let me take a tree of height h and n nodes. Yeah. So n is going to be larger than n of h because n of h is the smallest possible, is the minimum number of nodes that are possible in a tree of height h. N of h is that quantity.
What is n?
This is just a function. Don't confuse this n with the number of nodes. You can replace this n with something else.
The n of h is the minimum number of nodes.
N of h is the minimum number of nodes in a tree of height h.
But then what is n? So you said that n of h is less than n.
Okay, if you are getting confused, let me just clarify this. So what we argued here was that h is less than 2 times log of n of h. Yeah. Okay. Now take an AVL tree of height h and let us say, let me not call it m, let me call it m nodes. Yeah. So its height is h, it has m nodes in it. So what does this imply? M is greater than n of h. This follows from our definition of n of h. M is more than, and we know that h is less than 2 times log of n of h, which is then less than 2 times log of m. This implies h equals big O log of m. Yeah, the height. So what was this? This was height and this was number of nodes. The height of an AVL tree on m nodes is less than 2 times log of the number of nodes. Is this clear now? So the m and n confusion is not there. Great. So that's what is being said here. Any questions till this point? Yeah. So we've shown that such a tree will have height no more than 2 log n. The best possible tree could have height only log n, right, if it were like a complete binary tree, very dense and everything. But this has more height, but not too much more, just a factor 2 more. Much better than having a height of an n. Great. So let's try and solve this recurrence slightly better. This is more of an exercise also to show you how recurrences are solved, right. So we did a fairly crude analysis here, right. We replaced this with n of h minus 2 and then we did this and we got thing. Let's try and get something better, right, just as an exercise. So we'll show how to get a sharper bound on the height of an AVL tree. Abhi hamara kya bound aaya tha? The bound we obtained right now was 2 times log of n. Let's see if we can get something better than that. So we are going to use induction and we are going to do a tighter analysis of the same thing. We are going to show that the minimum number of nodes in an AVL tree of height h, which was n of h, is at least c times h. Now we are going to show it is at least c times h, where c will be some constant more than 1. What did we show in the previous slide? It was at least, n of h was at least 2 to the h by 2. 2 to the h by 2. So what was the c? Root 2. 2 to the half to the h, right. So there we showed a c of root 2. Let's see if we can get a higher c, right, a larger c, more than root 2, right, and what would be the way of doing such a thing. So, we will assume that n of h is at least as large as c to the h. Let us see what we can argue here. Okay, and we are going to prove this by induction, and we will figure out what the c is later. So, we are proving a certain statement without actually knowing exactly what the statement is, because I am not telling you what the c is, but you will see what the c has to be for this statement to be true. Right. So, what is the base case? H equals 1. H equals 1 pe n of h is 1. We want that. So, this statement would be true. This statement is true at h equals 1, right? No. Just one second. What have we said? We have said that the number of nodes is going to be at least as large as.
There will be some multiplication by some constant. Yes, a chain to c to the power h would be right.
Okay, let's come back to this in a minute. So, I seem to have made a mistake here. Let's come back to this base case again. Right, we will have to perhaps redefine the height of a tree here. Okay. Right, I think maybe we should have c of h minus 1 or some such thing. Okay, we come back to this. Suppose the claim is true for all h less than k, and let us try and prove it for h equals k now. So, we have to prove that n of k is greater than or equal to c to the k. Okay, we will come back to this base case in a minute. Okay, so recall this was our recurrence relation, m of k equals n of k minus 1 plus n of k minus 2 plus 1. Our induction hypothesis says that n of k minus 1 is at least c to the k minus 1, n of k minus 2 is at least c to the k minus 2, and I have ignored the plus 1. So, actually I can say that this is strictly larger, right. I will just ignore that plus 1 again. Okay. Now, I have to show that n of k is larger than c to the k. I can show that n of k is larger than c to the k if I can show that this quantity is larger than c to the k. Yeah. So, this is what I have to show. I have to show that c to the k minus 1 plus c to the k minus 2 is larger than c to the k. Yes. Right. Okay, good. So, what should c be so that this is true? Well, I just cancelled out terms appropriately and I get c square minus c minus 1 should be less than or equal to 0. If c satisfies this, then this will also be true. Yes. Why? Because I just multiply both sides by c to the k minus 2 and I would get exactly that. And if this is true, then n to the k, which is larger than this, would also be larger than c to the k. Right. So, I just have to pick a c which satisfies this. Right, and you all know how to figure out a c which satisfies this, right. So, we will just solve this quadratic equation. This has roots, right, 1 minus root 5 by 2 and 1 plus root 5 by 2, right. This is negative. So, anything in between would keep this less than 0, right. But I want as large a c as possible. So, I will take 1 plus root 5 by 2, which is roughly 1.63. Right. This quantity is also known as the golden ratio. Okay. So, we will see this more often perhaps.
So we can solve it exactly.
We can solve what exactly?
So, add 1 to both sides and assume nk plus 1 is some function of k. So you will get mu k equal to mu k minus 1 plus mu k minus 2.
nk plus 1 will satisfy the Fibonacci relation.
So
No, this is not the Fibonacci relation,
Yes.
So
right?
if
This
you add
is
1
So
on
nk
both sides, then n of k
we
plus
can
1 will
obtain
satisfy the
that.
Fibonacci relation.
if you add 1 to both sides,
Then you club 1 with each of the term.
right? Okay, good.
Then write some other function f equal to n of k plus 1.
Okay,
Then f is the Fibonacci number.
good. Okay,
And n is Fibonacci number minus 1.
Okay, so you will get n of k would be the Fibonacci number minus 1. Good, yeah, you can also do that. Right, so we get a bound of roughly 1.63. C as 1.63. Right. So what is the mistake we have made? So one thing is our base case has not worked out, right? So I guess this was the wrong thing to pick. It should not be c to the h, but maybe c to the h minus o1. Right. So induction hypothesis should be c to the h minus o1.
So if we take k c to power h, it will include that case also.
1 by c is also constant. Yeah.
Right. So let's just take c to the h minus 1. It will not make a difference. Right. So you take c to the h minus 1. So essentially I am dividing out by c. Then the base case would also be satisfied. For h equals 1, you would have more than 1, which is the case. Yeah. And so sorry about this. And for the other 2 also it will be okay. Yeah, because for h equals 2, n of 2 is 2, and this would become c to the 2 minus 1, which is c. C is less than 2 because we just argued it is 1.63. Okay, so please make that correction. You really require that the induction hypothesis is h minus 1. It will not make any difference on this, however, right? यहाँ पे अगर k minus 1 हो जाएगा, if this becomes h minus 1, this will become k minus a 1, right?
Sir, or we could have said
This would continue as it is, right? This will become k minus 2 plus c k minus 3. We have to prove this is greater than or equal to c k minus 1. Everywhere there will be a minus 1, so that you will still get the same quadratic inequality. Yeah. So the value of the c would still turn out to be the
At the
same.
end we get nh is greater than equal to 1 to the power
1.63 to the power k minus 1, h minus 1, n of h. Yeah. So please make that small correction. Okay. And so you will have that the AVL tree on n nodes has height now log of n to the base 1.63, this quantity. Right? Because what have we said? We have that if I take a tree on n nodes, the same argument as before. So we just do the same argument as before. We have, I take a tree of height h and n nodes. Yeah. So we have just seen that n of h is greater than or equal to 1.63 to the h, let us say minus a 1. That is what we saw just now. This is the tree with the smallest possible number of nodes. So n is going to be only larger than this. Let us take log of both sides. So we get log base 1.63 n equals h minus 1. I am just using the definition of log. I am taking log to the base 1.63. Yeah, so I will get this. This implies h equals log of 1.63 n plus a 1, which is okay. Right. So we have been able to prove this kind of a sharper bound. Yeah.
So this equation doesn't satisfy n2.
This equation does not work for n equals 2. It does? Okay, great. It also works for n equals 2. Right? So that was our base case. Is everyone with me? Okay. Great. So let's continue. So I've shown you 2 ways of solving the same recurrence, right? One was a much simpler way. Actually, both were very simple, right? So the second technique is also used quite often. You make a guess on what you think it should be, the right value should be, right? And then you essentially verify that. So we said, suppose the right value is some c to the h, yeah, and then you figure out what your c should be, and you can get something better, right? So earlier we had root 2 1.414, and we could up it to 1.63 by using this kind of a technique. Okay, so let us look at the structure of an AVL tree in a little bit more detail, right? So I once again have an AVL tree on n nodes. Okay. Now let me take the leaf, that leaf of this tree which is closest to the root, which means whose level number is as small as possible. the smallest amongst all the leaves. Suppose this leaf is at level k. Okay. We can show that the height of the tree is at most 2k minus 1. Is this clear? No, this requires a proof, and let us do that. Okay. So, what have I said? I have an AVL tree which has n nodes in it, although this is not going to be particularly important, the number of nodes in the tree. So, this is some tree. Okay. I took that leaf of the tree which is closest to the root, right. Suppose it is this leaf here which is closest to the root, and we said it is at level k, right. So, the other leaves could be at this level or could be below.
So now we are taking root as 0 level.
No, in this class for AVL trees, let us say we work with level starting 1. Does it make a big difference? Let us say we start with level 1. We are going to prove that the height of this tree is at most 2k minus 1. So, height of this tree is less than or equal to 2k minus 1 is what we will prove. Let us see why. So, I will draw this picture again here. Okay. So, this is the leaf, let me color it red, which is at level k and which is the one which is closest to the root, right. From this node there will be some subtree hanging out from this node, yeah. From this node also there will be some subtree hanging out, and so on and on. This is my root, level 0. Oh, level 1, sorry. Now, let us look at this node first, which is at level k minus 1. What is the height of this node? What can be the height? Well, it has one child, this child has height 1, this has height 1, so the heights are in blue, yeah. So, this means that this subtree can have height at most 2. Right. So, we want to get as large a height as possible for this tree, right. So, whenever we say at most 2, we will just take the largest value, right. So, this can have height 2. So, if this has height 2, what is the height of this node? This subtree will then have, this subtree will then have height 3, yeah. This subtree will have height 3. If this subtree has height 3, what is the largest height that this subtree can have? 4. So, what is the height of this node? 5. So, what is the maximum height this subtree can have now? 6, and so this would be 7 and 9 and so on, right. So, what will the root have height now? No, in general, given that this was k, yeah. So, well, right, if, yeah, just figure it out, it should be 2k minus 1, right. If it was just till up till here, then it is basically k2 height 3. So, when if k were 2, this was the picture, then the height was 3. If k was 3, this was the picture, height was 5. If k was 4, height was 7, and so if for arbitrary k, this is 2k minus 1. Yeah, very simple argument. So, which means that this entire tree can be no taller than 2k minus 1. If the closest leaf was at level k, This is a property of AVL tree. It's not a property of any arbitrary binary tree. Yes, you understand that, right? In an arbitrary binary tree, you might have leaves at any level, but the height of the tree could be as bad as you wanted. Here is a leaf at level 1, but इसकी height आप कितनी भी बड़ी बना सकते हैं, right? But for an AVL tree, if there is a leaf at level k, then the height of the tree cannot be more than 2k, right? So an AVL tree is basically if there is a leaf at this height, if there is basically all our leaves now will be in this part only. This band whose width is as large as this roughly, right? This was k and this was also k. K minus 1, I am ignoring that. Yeah, I will come back to this in a minute. Okay, so we just argued that if the closest leaf is at level k, then the height of the tree is no more than 2k minus 1. That is the largest possible height the tree can have. Okay. Now let us make another claim. If the closest leaf is at level k, then all nodes at levels 1 through k minus 2 have 2 children in them. Every node on these first k minus 2 levels have to have 2 children, right? And why have I said k minus 2 and not k minus 1?
K minus 1 node has the leaf.
If you have one children, K will be that children
Right.
will be the
So let us prove this by contradiction. So what do we want to contradict? So let us take some node at level k minus 2 which has only one child, right? This is the picture. I have a node u level k minus 2, it has only one child which is at level k minus 1, right? I have shown a node at level k minus 2, but the same argument would apply to any node at 1 through k minus 2. Yeah. So V is at level k minus 1, so it cannot be a leaf because our closest leaf was at level k.
Then this will disrupt the AVL.
Right? Good. Yeah. So it has to have another child. I have shown only one, but it can also have 2 children. No harm. Right? But this guy U has only one child.
Height balance property value.
So subtree rooted at V has height at least 2. Yes? Because this has to have one child. It cannot be a leaf. So it has height at least 2, while the right subtree here has height 0 because there is nothing there. So you have a height imbalance at this node U. So the height balance property is violated at node U. Yes? So every node on these levels 1 through k minus 2 have to have 2 children, right? At level k minus 1, however, there can be nodes with only one child. That you understand, right? Everyone understands that? This is level k. Of course, the tree extends. This is the level at which the closest leaf is. At level k minus 1, I can have a node with only one child, and that child is this, let us say here, right? This is okay, provided this guy does not have any more descendants, and it need not have because it can be a leaf, right? So this is completely okay, but if it had more descendants, then we would again have a problem, height balance property. Yeah. So this is okay. So which means that this guy can have only one child, but everything here has to have at least 2 children. Okay, great. So we said every node at level k minus 2 has to have 2 children. So which means levels 1 through k minus 1 are full. Full means they have as many nodes as are possible on a level, on that level in a binary tree. This is after all a binary tree. Right? So they are full. So what does that mean? That means that the tree has at least 2 to the k minus 1 nodes. Yeah? We also argued, recall, that the height of the tree is at most 2k minus 1. So if the height of the tree is 2k minus 1, then it has at most 2 to the 2k minus 1 nodes. Yeah? This implies the number of nodes in the tree, which was n, is between 2 to the k minus 1 and 2 to the 2k minus 1. Yeah? Everyone with me? So since we've been using h for the height, right, let's substitute h for 2k minus 1. Let's see what this equation will look like. This becomes 2 to the h and this becomes 2 to the h minus 1 by 2. It's the same thing I am showing you over and over again. What is this saying? If you have a tree of height h, an AVL tree of height h, then it has at least 2 to the h by 2 nodes we had shown earlier, right? So now we are showing 2 to the h minus 1 by 2, just roughly the same thing. Square root 2 to the h nodes. Although if you proved a sharper bound, I am coming back to the older bound. The point is, it has an exponential number of nodes. It has a number of nodes which is some constant c to the h, an exponential, right? Because that's what gives us the logarithmic height property. Right? So this is actually a third way of proving that the height of the tree is only log n. Right? You can also use this as a proof. Right? This did not require solving a recurrence relation. The other two methods we saw were solving recurrence relation, but the sharpest bound we have seen so far is c to the h, 1.63 to the h. So let's summarize what we have seen as far as the structure of an AVL tree is concerned. So if the height of an AVL tree is h, then the closest leaf can be at level h plus 1 by 2. Right? I have just changed things around. When I said when the closest was at k, then the height was 2k minus 1. So I just changed that around and I said if the height is h, so suppose I give you an AVL tree on n nodes in height h, then the leaf which is closest to the root is actually pretty far from the root. It is at least half the height away. It is at least h plus 1 by 2 away. Yeah? This does not require a proof, it is just I am just rewording what I had said earlier. We also saw that on the first h minus 1 by 2 levels, the AVL tree is a complete binary tree. Right? So this is what an AVL tree looks like essentially. For the first half of half levels, it is complete, very dense, yeah, and then it starts thinning out. Right, as it starts, so you turn the tree around, so with the root at the bottom, so initially it is dense and then it kind of thins to the full height. Right, but this part, the fact that it is very dense for the first h by 2 levels means that it has a lot of nodes. It is a complete binary tree, so it has 2 to the h by 2 nodes straight away. Yeah, and that means that the height cannot be too large. If I had n nodes, the height cannot be more than log n, 2 log n. Right. So once again I have said that if number of nodes in the AVL tree is at least just from this fact, since it is a complete binary tree on h minus 1 by 2 levels, it has at least 2 to the h minus 1 by 2 nodes and at most 2 to the h nodes, because that is the height of the tree. Okay. So this is a useful structural fact to keep in mind about AVL trees, although we will not use it for any of our algorithms, but it just gives you some intuition of what the tree is and why is it that this tree has only a logarithmic depth. Yeah. So, now we have looked at this height balance property, right. We said, if this height balance property is there, then it's nice. The height of the tree is only logarithmic, and so now we want to say that all our operations are only logarithmic, because we still want to say that you can do your search, insert, and delete in log n time. So search is easy. There is no problem with search, right? Because after all, it's a binary search tree, right? Forget the height balance property. It's just a binary search tree. So you just do the search as you do in a binary search tree. How much time will you take? Proportional to the height. Order edge. Height is log n, so you will take only log n time. Yeah, great. That's the best you can do in some sense. Okay. Now suppose you were to try and insert, right? Suppose so when you were going to do an insert, what can go wrong? So recall that we call this height balanced, a tree to be height balanced if the difference in the heights of its children is at most a 1. So when I insert a node, it can change the height of some nodes, yeah, and as a consequence the height balance property might get violated. Okay. So when I insert, so insert will be the same, the first step of insertion would be the same as we did in the case of a binary search tree. Yeah. How did we insert in a binary search tree? Can someone tell me?
First you find the position.
First you find the position. How do you find the position? Well, you just search for that element that you are trying to insert. That will tell you where the position is, and you just put the node there. Put the node there, and then you start marching up back to the root by following the parent pointers. Okay. And as you march up, you keep updating the heights of the various nodes you encounter, because these are the only nodes whose heights could have changed, no one else. Yes. So these are the only nodes whose height. We will look at this again in more detail perhaps in the next class. I am just giving you a flavor of what needs to be done when we are doing an insertion. So these are the nodes whose height will going to change. So we are going to go to the first place where a height change appears, where a height imbalance happens.
Could you repeat the last statement? Which all nodes are we supposed to check?
We are going to only start from the node where we inserted and move up the tree towards the root. So basically keep going parent, 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 parent till we hit the root. And on this path that we follow, we find the first node which has the height imbalance property, right. So suppose that node is called Z and its grandchild is called X. Okay. Let me skip this part, and Y is the node in middle. So I think it's best if I show you a picture, and that will give you an idea. So suppose this was my tree, right. Forget this empty node for now. This was my tree originally, right. If this was my original tree, is it an AVL tree? Height balance is satisfied here because this is 1, this is 1. This is not there. Just forget this guy for now, right. This is also height balanced because this is 2 and this is 1. This is also height balanced because this is 1 and this is 0. This is height balanced because this is 2 and this is 3 initially. But now suppose I went and inserted a node, let us say 54, which came in here. Yeah, 54 would come here. I would go right here, left here, right here and left here. Okay. Now the height balance property is violated. So what I am going to do is I am going to go up the tree towards the root. Is the height balance property violated here? No. It is not, right, because this is 1, this is 0. Is it violated here? No. 1, 2. This is height 2, this is height 1. It is not violated here. Is it violated here? Yes, because this is now 3 and this is 1. So these numbers are the new heights, right. This is 3. So this is the first node at which the height balance property is violated. We call this node Z. Its child will be Y and its grandchild will be X. Now you will wonder which child of this node will be Y. Well, the child on the path that we have taken. Yeah. And now we need to do something to this tree to make it height balanced again. This is not height balanced, right. all the things we said about login and all would go out of the window if we leave the tree like this, right. So what we are going to do is we are going to rotate, do a kind of a rotation operation, and this will become my new tree. Okay. So in some sense what I have done is I have kind of moved this up, moved this down, and this 50 was here, right. It looks a bit mysterious. So that's what we are going to do in the next class, right. Understand how this rotation operation is done. So as you can see now, the height balance property is not violated at any node. Yeah. So it's not clearly here, it's not here, it's not here. Both of them have height 2. This also, this is height 2, this is height 3, and this is height 2. So it's not violated. This is still a binary search tree with the same keys as before. We have not changed the keys, right, to make it.
So is this the only possible way, or can we do this?
There are other ways also, right? But this is, you want an automated way of doing it, right? You should not have to look at the, you don't have to draw the picture and then figure out what rotation has to be done, right? So you will be able to do this program. So this is what we are going to do in the next class. Look at insertion, look at how to do these rotations so that the height balance property is retained even after insertion. So we'll look at both insertion and deletion in the next class. So in today's class we looked at AVL trees. We saw how AVL trees are defined, and crucially we saw that the height of an AVL tree is no more than, actually we proved a bound of log n to the base 1.63 today, right. We spent a lot of time figuring out how to solve that recurrence relation. So we saw 2 ways of solving that recurrence relation. We also look at some structural property of the tree which also proved a similar bound on the height of the tree. Yeah. So with that we'll end today's class.